afternoon, everyone. So I'll be Assistant Professor Abderrahmane, the session chair of this parallel session about artificial intelligence and computational systems. So I am Salma. I'm a postdoctoral researcher in UMSXP. I'll be also presenting for this session. And I'd like to present Mr. Carlo Lucheroni. Sorry. He's going to present the first session and his research work entitled Electricity Market Time Series Forecasting by Machine Learning Methods. So I think you have 12 to 15 minutes for presentation. Okay, we'll do.
Make this.
Okay, so I'll give you the...
Okay, thank you. I'm Carlo Lucheroni, University of Camerino. Camerino is a university in Italy, central Italy, and being in Italy, we turn on our lights using the Italian power system, which means the Italian electricity system. Sounds as a very technical thing, right? But I mean, in this community, which is, I think, is interested in complexity science and understanding things that cannot be easily taken down just to small and a few interacting parts, I'm going to try to convince you that behind that little act of turning on and turning off the light, a complex system is activated, but a complex system that consistent that you can study just by looking at pictures. A complex system which is really simple behind all that machinery. So we will go through many technical details because what I'm going to present you is really technical from a certain point of view. It has to be because it is connected with techno-social system which is complex by itself, but and thus I will need to tell you a story and illustrate how this system works. Only at the end of my presentation I will show you what this system is really or appears really, and that will be at the very end of the presentation. I will go through, okay, can you see the red spot? Okay, maybe not. So I will go through some technical introduction about how this market works, the electricity market, and I will tell you something about the system I propose, which is completely new in the literature, probably the only one which is able to do that. And I will talk a bit about what you can do with the results of the model. And then I will get to my conclusions. Of course, all of you know what an electricity system is. Basically, it's a system which is made by users, houses and things like that, and producers. But nowadays, these systems rely very much on a financial layer in which producers and wholesale customers cross their bids about I want that much electricity, I want to sell you that much of electricity, are traded in a sort of pit, which is a stock market, a real stock market. The stock market in this specific case is called DAM, day ahead market. We will see what that means. But the point is that, yes, there is a layer in which individuals take decisions, bidding into the market, a top layer in which prices are formed, and this is what you pay for your electricity bill, and an intermediate layer, which is usually not recognized as extremely interesting, especially for complex system communities. So there will be something here, hidden here behind, that could interest you. The mathematical object or data object I'm going to work with is something like that. We will see that picture again, but basically it is something that you already know. because it is the plot of two market curves, a supply curve and a demand curve that cross in between. Maybe you remember, or those of you who didn't work very much on economics know that prices very often are formed at the intersection of the two curves. So we have, again, three levels. One level, which is the interaction among agents who place bids. Okay? Top level, the price which is formed by the market operator, and in between these curves, made of a lot of points, a lot of data. They are very, very much data rich. Again, this kind of market is the same all over continental Europe, UK, but most of the countries in the world. They are called day-ahead markets, and they are managed mostly by a market operator, an entity which works like the stock exchange for requests for electricity and production of electricity. It's a huge market. The Italian market is part of the European market, and the purpose of having this operator here is, as we said, coming up with clearing prices, which means the prices you see at the end. Actually, these are wholesale prices, but retail prices follow those kind of prices. So, in this market, which we could call, and we could call this description the micro scale of our problem, in this market, market agents like generators, wholesale retailers, technically called loads, sorry, the system operator itself, work and propose bids, financial bids. The point is that all this information is aggregated in a curve like okay, oops. It is low. It's not a problem. Okay, thanks. Thank you. Gets aggregated in that patterns we saw before, which are called supply and demand curves. This is an enlargement of this area here, and you see that since these dots, as I said, correspond to individual behavior, the whole curve integrates individual behavior because the agents talk to each other. The agent call one the other. The agent are in a market in which they forecast what is going to be the day next. So this is something that shows you how decisions are taken by individual agents. From this point of view, we have now three layers. We have the micro scale, the individual behavior, the macro scale, which is the prices, and this mesoscale. Nobody has, to my knowledge, ever studied this mesoscale in which you see how behavior is aggregated. Okay. The second thing I want to show you is how to model this system, which means mimicking the aggregated rational behavior of participants. And it is rational, and the system operator and the market operators know about that because traders try to trick the system very, very often. And the system operator or market operator is very much interested in understanding how the participants trick the system, try to play with the system. Okay. What I want to do is reproducing this behavior. Again, it's not obvious. In the literature, there are many approaches, but I would say that there are 10 to 12 models in all literature, and most of all of them try to reproduce these curves by gridding, creating a grid of data points, and then putting special values on the values of the grid. It doesn't work. Or they can try to use splines. I did it in another publication, and then you try with functionals to interpolate these things. That does not work very well. So I try to go directly to the problem and try to model the points of the curves themselves. We're talking about 10,000 or 20,000 points per hour per day, which means about 9,000 of these curves in a row, with one system, which means I cannot use standard interpolation. That doesn't work. But the challenge is exactly this, to model the system at its micro level. The system which is able, and I'll show you how it is able to do that, is a system that takes inspiration from large language models. We heard a lot about them today, yesterday, and so on. The point is that there are generations of these models. So what I'm taking as a reference model is the old version of an LLM, which was a encoder-decoder architecture, which works in this way. Many of you probably have this T7 in your cell phone, which means you start with a word and the cell phone completes the word, right? All of your cell phones working on this algorithm here, which means that your data come in some way the system is able to compress the data, recognize them, and then produce the rest of your word. Okay, so this is a very robust technology which works. Why can I use this kind of structure with this data? Well, you add a loop. Oops. You add a loop to that. Okay. You add a loop to that, closing this thing here, forcing the system to put into the output what it sees in the input. This is called autoencoder. This is not a standard autoencoder, doesn't exist in the literature, but it works the same, so that when you have a curve here, the system, and you will see why the structure is so much complicated, the system is able to output the same curve. It's not obvious at all. Then, once I have this, I can say that if the system sees a curve it has never seen before, it will come out with a curve which is plausible, which belongs to the set of curves that the Italian market can produce. I'm sure many of you saw that picture in which you see President Trump taken away by policemen. It's a meme, many people saw that. Okay? That means that you have a system in that case in which can pick up from the collective pool of images and extract another images, new, but which is plausible for your eyes. Because you're led to think that that is a reality. So this system works exactly in the same way. Once the system understands the curve, then it understands all curves, and then you can put in data which are not a true market curve, but it will reply to you with a true market curve. You will see why this is so much important. In any case, this is the technical structure of the system. It makes use of something which is not very often used in literature, like the Chamfer laws, a consensus decoder, two experts, then a competition between experts, one of the experts on the tail here of the market curve, which means renewable energy, and the other one on the other part of the market curve, which means peak gas, natural gas generators and things. So it's complicated a bit. I mean, it works. And the point is this. The system can ingest all this data coming from 1 year of Italian market. I can download it for free in Italy for whatever year I want. And automatically, without me having told the system to do so, being able to extract information from those curves and summarize these curves. You would would say, why so? Well, this is one of the examples. This is the what, more than why at the moment. The system, in black you have what is called ground truth, real points, and these other things, especially in purple, you have the response of the system. So this system is able to reproduce all the features of those aggregated curves. Okay, this is another example. It's incredible. In the literature, you cannot find this kind of curves. I mean, the curves, yes, but you cannot find such a detailed level of modeling. Here, it's impressive for me, because you remember that this curve gets crossed with the demand curve. I can predict the price in this way. But the point is that I can predict a price with a much more information than simply predicting the macro level. So again, below the decisions, I'm able to predict the decisions. Above we have the price level, which is the macro level, but in between we can play with the meso scale, the meso level. And if we have a model for the meso level, the model of what we think of President Trump, if you want, well, we can basically extract the guts of the market, how the Italian market works. I tried also with the Canadian market, how the Canadian market works. And in any case, you can get curves which are plausible, like the photography of President Trump and so on and so on. Which means that once I have this, I can go even beyond that. First of all, I have a digital twin of the market. Second thing, and this is the most important thing, is that can you imagine what can it be the dimension of this world in which market lives? Consider that I used about 800 points per curve. Well, the nice thing is that it boils down to three components only. With just 3 numbers, I can give you the exact reproduction of an Italian market curve, or whatever curve this Italian market would ever produce. So I can do forecasting. So I can do counterfactuals. What about tomorrow is not Thursday? Or Wednesday, or whatever? Then, in a sense, I can extract. So this is about the dynamics I can get on such a small dimensional surface. But what I can extract from this system is an learnable ontology. So there are words inside this system, because the system is able to automatically, I didn't tell it, extract what is a normal market, peak market, when prices are high, and so on and so on. So the system does it automatically. The system takes something which is very complicated, this mesoscopic scale in which you have hundreds of participants to the Italian market, and then automatically tell you what happens if. In words, I'm not talking about mathematics. So the trader can ask the system what happens if, and then get the reply. The second part of this work, which I already did, is forecasting. With the advantage with this method of forecasting something which is real, not just numbers that are close to other numbers, not just curves which are close to other curves, the real thing. So my conclusions are that these data curves that I think that do not appear in complexity science papers are very interesting for you. They are fingerprints of something very complicated going on. But yes, something very complicated, but which can be squeezed down to a very small amount of information. Because you have understood the surface, the manifold, where everything happens. Second, go to the bits. Don't go to the prices. Don't go to the gridding. Don't go to the standard. Try to attack or take on the difficulty directly. And for me, this is the most important part. The emergent expert specialization, you remember this expert, green expert, thermal expert, and so on. I mean, it comes only from PyTorch, from the gradient pressure alone, and not from me. It's the system that has understood what it means taking away President Trump. It's in your heads, but the system can extract it. And then the point is that associating to this, I can create an ontology, which means a logical system that can reply to your questions, and that's it.
I'd like to welcome Ms. Meryem Abtane for her research entitled Optimization of Sensor Placement for Detecting Ion Bearing Faults in High-Speed Trains.
Hello everyone. So it's a privilege to be here today to share our research on optimization of sensor placement for detecting axle bearing faults in high-speed trains. So this research is part of our project named Meryem, which is a collaboration between École Centrale Casablanca and Siana, which is a Moroccan company specialized in Moroccan high-speed trains maintenance. So this work was carried out as part of an internship completed by Gilbert Rabat. So it's a final year end of study internship, and today I will be presenting the key results and main findings of this study. So first of all, I will start with an introduction to Moroccan high-speed trains and their bougie systems. Next, I will detail the context and problem statement. After that, I will talk about the methodology. Next, I will present our results, and at the end, I will do a question and answer session during which I will come out of your inquiries and questions about this topic. So Morocco has made remarkable advancements in its railway systems with the introduction of high-speed trains. So these trains are capable of reaching speeds of up to 320 kilometers per hour, connecting major cities like Tangier and Casablanca. So here we obviously see a train, but if we dive deeper into its components, specifically the bougie system, we can find that it is composed of wheels, suspension systems, braking components, and here we have the axle box bearing. So axle box bearings ensures the smooth rotation of the wheels. So therefore the effective detection of these faults is crucial for ensuring the safety and reliability of high-speed trains. So as we examine the context and problem statements regarding the health monitoring of axle bearings, so it is important to consider existing practices and technologies such as hot box detectors. So hot box detectors are systems that utilize infrared sensors in order to compare measured temperature against a predefined threshold. However, the effectiveness of these systems can be impacted by climatic conditions such as rain, snow, or extreme temperatures, which may distort temperature readings. Also, the detection may not be early, as a natural bearing defect must be sufficiently developed to generate a noticeable increase in temperature. Also, minor defects may go undetected due to the threshold-based detection. Another common practice is auditory and visual inspection of bearings anomalies. However, human error represents a significant risk, as it relies heavily on technicians' expertise and subjective judgments. Also, we have some limitations in identifying hidden bearing defects. So the objective of our study is to enhance axial bearing fault detection by strategically identifying the optimal position of vibration sensors. So here we have a bearing that is composed by outer race, inner race, gauge, and rolling elements. Each component has its own characteristic frequency, which depends on bearing geometry, such as number of balls, contact angle, etc. And the objective is to detect the presence of these characteristic frequencies in the signal, as this would indicate a corresponding fault in the bearing, and ultimately helps us find the optimal sensor position. And for the methodology, we start with the signal collection from our complex systems and interactions test rig located at Ecocentral Casablanca, where we have a motor that drives the bearings, while a speed controller adjusts the motor speed, allowing us to test bearings under various conditions. We have also an accelerometer, which is connected to an acquisition card from national instruments. And for data acquisition, and storage also, we use the LabVIEW software. And here we consider three main positions, which are vertical, horizontal, and horizontal offset. The horizontal offset configuration was secured using a hot melt adhesive in order to preserve a no-hold setup. So data collection was done with three main speeds, 10, 15, and occasionally 20 Hertz, with the loaded and unloaded conditions, and for a lot of bearing faults, such as the outer race, inner race, and ball faults. And after data collection, we use many signal pre-processing or processing techniques, such as filtering, Hilbert transform, frequency analysis, and we use for this the well-known statistical indicator, which is the kurtosis. So the kurtosis indicates how sharp or flat the signal peak is and helps us detect impulsive events. Here we have healthy bearing. So the healthy bearing signals is characterized by remarkable regularity, very few fluctuations, and a stationary and of low amplitude. Here we move on to the frequency representation of the waveform signals, where we have the first observed peaks represent the harmonics of the motor rotation frequency, which is of 20 Hertz. And in the following, we will mainly focus on defective bearings to analyze the effect of sensor placement on fault signatures. So to do so, we use the many bearing faults. So here we illustrate the outer ring fault. So for the time domain, we can find the cyclostationary impulsive signature featuring periodic shocks from the outer ring fault. And as a conclusions, we can say that the vertical radial position stands out among the others, and also the horizontal radial position is more pronounced than the non-radial one. And here we move to the frequency domain of the outer ring signal, where we can clearly find peaks of the fault frequency, also its harmonics. So here we consider an outer ring fault at 10 Hz speed, and the corresponding fault frequency is of 30.48 Hz. And we can say that the vertical radial position spectrum is clearer, isolating the harmonic from background noise better than the other position. Here we move on to the kurtosis analysis. So for the right side, we have the kurtosis analysis of the healthy bearing. So the values consistently hover around 3, which is the value for Gaussian distribution. And we can say that the signal is normal without any significant impact. However, on the left side, the opposite, the right side, we have the kurtosis analysis of an outer ring fault. So the values are between 10 and 18 for the vertical sensor, and we can say that this massive increase is a direct result of the repetitive high energy impacts we saw in the time domain earlier. Here we consider the loaded conditions, or a test bench under load, and we will be focusing mainly on the frequency analysis, and compared to the unloaded case, the amplitude increase significantly, and the spectral peaks become more prominent. Here, after many laboratory tests, we moved on to field tests with defective axle bearings from removed axles in the Siena Technic Center. And the axle was mounted on a jack, and the acquisition devices were connected similarly to the previous test bench. And here the accelerometer is mounted on the bearing using a magnet, and we consider 3 main positions, which are the middle radial position, the lower radial position, and the near the wheel position. So here we analyze the acquired signals from the 3 sensor positions. For middle position, we can clearly see the signal shows attenuated signals and reduced vibration due to structural damping, while the lower position in the middle displays high sensitivity and impulsive events. And finally, the near the wheel position presents high sensitivity also and clear impulsive events and peaks, serving as a critical point for early fault detection. And here we analyze the kurtosis of the 3 signals. So the kurtosis value from bottom and near the wheel positions clearly indicates the presence of defects in the bearing. And we can say that sensor placement significantly impacts signal clarity, with bottom and near wheel positions being the most sensitive to detect defects. So thank you so much for your attentions.
After that, we take the role of chair. Thank you very much, Salma, for sharing the first part of the session, and we move to the third presentation for the Salma and Ariche to present the work embedded Mamdani fuzzy control of HVAC system in battery electric vehicles.
Thank you, Professor. So I'm presenting a work I have conducted last year during my PhD thesis that was held in both Qadiyat University and Paris-Saclay University and was funded by PhD Toubkal, represented by Campus France and CNRST. So the work is entitled Embedded Mamdani Fuzzy Control of HVAC Systems in Battery Electric Vehicles. And the outline is as follows. I'll be presenting an introduction by identifying the context, motivation for the research, methodology of our proposed solution, then results, and finally a conclusion. So electric vehicles are becoming, or maybe have become, a major direction of the automotive industry, as they represent a break with the traditional technology based on combustion, internal combustion engines, and also they present a growing share of the global automotive market. Especially that they have many advantages, such as zero emission during driving, also faster and simpler maintenance. Also, they are backed up by advances in technologies. Now we're talking about range that can go more than 500 kilometers for only classic battery electric vehicles, and a medium charge less than 1 hour, even a faster charge less than 20 minutes. However, they still have constraints. They are limited in autonomy despite technological advances. Recharging time is still longer than refueling time. Like for a classic vehicle, refueling time takes only 5 minutes at most. And they are very or highly impacted by climatic conditions. So as a consequence, we have a driver that has to carefully plan his long journey. Many drivers can also face range anxiety, which is the fear of running out of energy during the journey, and impact on consumer adoption of this technology. It is important to know that when we talk about battery electric vehicles, we have the electric powertrain that accounts for 60 up to 80% of total energy consumption, while thermal auxiliary system can go from 20% up till 50%, depending on operating conditions, even in critical situations. Knowing that battery electric vehicles are very or highly impacted by what we call in literature impact factors. So for a natural environment, they are impacted by cold weather and hot weather. For an artificial environment, they are also impacted by the urban way of driving, traffic congestion, and even vehicle parameters. We're talking about battery discharging or degradation, and even the driver behavior could highly impact energy consumption. So it is important to understand the impact factors to design the best energy management system dedicated for such vehicles. In fact, in the state of the art, we have classified the systems into 4 categories. We start by rule-based strategies like fuzzy logic control. We can go to optimized-based strategies that could offer online and offline optimization, such as dynamic programming. More in a better intelligent way, we can talk about learning-based strategies. We talk about neural networks or even reinforcement learning. And finally, the most explored category currently is the hybrid combination of rule-based online optimization, optimization-based or learning-based methods. However, research gaps remain. We have, for example, optimization learning-based strategies involve complex computation and are not suited for real-time management. Also, energy management system based on AI requires significant computational resources, and hybrid learning-based studies lack consideration of most of driving impact factors. And finally, studies dedicated for battery electric vehicles, so I'm talking about mono-source energy, remain rare. So in this context, what we propose is a supervisor. It's an intelligent supervisor. It's a data-driven model which takes information from the data of the vehicle, of the environment, the driving preferences of a single trip, and this supervisor takes the request of the power of the main consumers in a vehicle. We're talking about electric motor and HVAC system. So the supervisor should control this distribution by allocating energy depending on the data-driven model. At the last edition of this conference, we have presented the results of the fuzzy logic control of the electric motor. They were very optimistic results, so we thought that it would be very interesting to extend the study and do the same with the other main consumer inside the battery electric vehicle, which is the thermal system the HVAC system. So what we're using is the fuzzy logic approach. So basically, this controller of a significant potentially energy management system for electric vehicles under condition of uncertainty and nonlinearity in energy demand. They can process imprecise inputs. So what we have is we do not have numerical inputs that we can feed the system. So fuzzy logic is the best solution we could use. We could give the system intervals, and he's going to do the inference and give us the solution or the output we're looking for. So dynamic management of power flow across vehicle components in response to varying driving conditions and environmental factors. This is another or a better visualization of the system. So what we are feeding the system as input is the state of charge of the battery. It goes from 3 states: low, medium, and high. We have the driving mode. We selected 4 common driving modes as sport, eco, comfort, and normal mode. And finally, temperature that has obviously 3 states: cold, normal, and hot. So after the reasoning, the system gives us an output, which is a coefficient that has values in range of 0 and 1. And basically, the coefficient just tells us how much energy we will allocate the HVAC system, or what is the priority in every case for the HVAC system. So first of all, we will evaluate our system on generic data on MATLAB. So we have compared results between 2 main inputs. For example, in the first figure here, we're trying to compare the coefficient response between temperature and driving mode. Like, for example, when the temperature is in normal mode and the driving mode is eco sport, knowing that eco is to preserve energy, in sport we give priority to electric powertrain. So the coefficient has very low values. However, when we go to comfort mode, if we are in a cold weather or very hot weather, the coefficient exceeds 0.6. Same when we have compared between the driving mode and SOC. If the state of charge is in low levels, the system is basically deactivating the HVAC system. But if we are in HVAC mode and SOC is very high, the coefficient gets to go up to values that exceed 0.6 threshold. After this evaluation, go into the second step of our testing. Now we're testing on real-world driving data. So we have selected trips from the dataset Munich 20. It's a dataset that has records of 72 trips of a BMW i3. The trips are recorded between category A, which is hot weather, and category B, which reflects very cold weather. For example, we have here the trip A32, and we have selected the following driving modes. At the beginning of the trip, we have selected comfort driving mode to ensure thermal comfort for the driver, for example. And we can see that the coefficient always has higher values, so it's always exceeding the threshold, which is 0.6, especially that when we go up to 30 degrees Celsius, the coefficient has a value that's very near 1. So it's basically telling us that HVAC system has a bigger priority. By the end of the trip, we have thought that maybe eco would be the best option for the driver if he likes to preserve more energy. So we can see that the coefficient values drops to very low values that are near 0. Also, for the second trip, which reflects a very cold driving condition, we have managed to do the same evaluation. We have selected comfort mode, especially that the temperature are very low at the beginning of the trip, and we can see that the coefficient has a bigger values. And then we have selected sport mode, just to say that the driver may be preferring to give priority to the powertrain, and there we see the coefficient values are dropping. And finally, as the state of charge has very low values, the coefficient also drops to very small values, we can say even null values. So now we have tried to test on generic data, on real-world data. So basically, the coefficient follows the requirements, and it has a dynamic response. It gives lower values when we have to. And now we think that the FLC coefficient could help us adjust the power requirements of the system. So what we're doing is the following reasoning. We start by calculating the HVAC coefficient by the fuzzy logic system. So if the coefficient exceeds 0.6 and the driving mode is comfort, the driver is free to choose whatever target temperature he wants. If not, if the condition is not valid, we go to the second part of this reasoning. If the battery state of charge is lower than 35%, we have a condition which is HVAC deactivation. If not, if the SOC is bigger than 35%, here it's the supervisor who chooses the target temperature. So basically, if we are in cold weather, the maximum temperature would be 18%. If we are in very hot weather, the minimum temperature would be 25%. And therefore, we calculate a new thermal coefficient, which is Q, and we can manage to adjust the power. So basically, this is what we call a backward validation. We have tested this reasoning on the selected trips, and we can see that for the first selected trip, A32, we managed to have 9% of energy saving. And for the trip B10 and B11, we can go up to 80% energy savings by only controlling on a data-driven level the HVAC system. The third step of our evaluation is the hardware implementation. So we basically deploy the system on hardware architecture to see the real-time response of the system. We use two nodes, so two STM32 and two CAN transceivers. The first node holds the database, so basically it's stocking database or reading database directly from sensors or a source file. And the second node is the MCU, where we have deployed the HVAC fuzzy logic controller. However, knowing that we have a temperature that goes from minus 10 up till 50 and SOC from 0 to 100, we have 6,000 coefficients to calculate. And each coefficient is stored as a float data type, so it's 4 bytes per coefficient. In total, we have 24 kilobytes. So when we have tried to calculate the time it takes to have a coefficient response for a clock frequency of 80 megahertz, we are in 8 million cycles, which could be translated to 106 milliseconds. This is still huge, so we thought of optimizing the system. So it's a very simple optimization. What we did is we stored the coefficients in lookup tables, and we basically scaled the system. So we multiplied by 100, then we converted to integer values, and when we stored the coefficients as integer values, it only takes 1 byte per coefficient, which in total give us 6 kilobytes. And we have gone from 8 million cycles to only 134 cycles, which can be translated to 106 milliseconds to only 0.12 milliseconds for our response. And here lies the complexity. The complexity was to find the most suitable algorithm that could be deployed in a hardware architecture and to have real-time response. So as a conclusion, we have designed the HVAC or thermal control management system to optimize energy consumption. We have calculated the computational performance, and we have seen that only from fuzzy logic, the processing time was huge, so we had to optimize. If we have used advanced technologies or advanced algorithms, we would be imposed to use more advanced architecture that could literally consume the energy we have saved. So for our future work, we would like also to extend the study on more auxiliary load and to evaluate real-time performance. And thank you.
Thank you, Salma, for your presentation. Thank you very much, Salma, for your presentation. And now we move to the last one, presented by Abderrahmane Boudribila. Automation, PLC code generation from textual requirement specifications. Thank you.
Good morning, everyone. My name is Abderrahmane Boudribila. I'm a PhD student at Qadi University. Today, I'm here to present our work entitled Automated Generation of Structured Text from Natural Language Requirement, a multi-agent transformer-based approach This research was conducted with my colleagues, Professor Abdulwahid Tajer and Professor Zakaria Belghassoul. So the structure of our presentation is as follows. We will begin with the introduction, move on to the state of the art, outline our objective, then proceed with the methods, present the results, and conclude with the conclusion and the future work. So, introduction. In previous years, industrial production lines produced the same type of products thousands of times. However, to survive in today's market, we have switched to producing a wide range of products on the same production line. This diversity of manufactured products and the ability to adapt to changes in demand has led to both planned and unplanned downtime, as well as error rates during the design of the control program. And to solve this problem, today there are two types of solutions studied in the literature. The first approach is the manual design, which refers to the process of intuitively writing PLC programs based on the knowledge and the experience of the programmer. This method is the most commonly used in both engineering schools and industry due to its simplicity. As you can see on this graph, the process begins with the manufacturing system. Then an expert writes a requirement specification outlining the desired behavior. From there, the expert designs a control program and simulates its behavior. If the simulation reveals errors, the expert must modify the control and simulate it again, repeating this process until the code is correct. After verifying the code, the next step is to transfer the code to the PLC, which will then control the input manufacturing system. While this approach is popular for its simplicity, it presents a lot of challenges. Firstly, the complexity, which refers to the process of, which refers to the difficulty in understanding the requirement specification. Secondly, time consuming, which means that the process requires a significant time and effort. Thirdly, error prone, which refers to the higher probability of making errors. Fourthly, maintenance, which refers to the challenges associated with updating and modifying the code. And lastly, the steep learning curve, which refers to the significant time and effort needed to become expert in manual design. To solve these problems, researchers have switched from manual to formal design, which refers to writing PLC programs based on formal method, such as supervisory control theory or other mathematical approaches. This method is the most commonly used in research due to its systematic approach. As you can see on this graph, the process begins with the manufacturing system. An expert writes a requirement specification outlining the desired system behavior. From there, the expert designs a formal model of the system behavior. After identifying the system components, these components can be actuators, pre-actuators, sensors, or effectors. In parallel, the expert designs a formal model of the constraints. These constraints can be security constraints, what the system should not do, and liveness constraints, what the system should do. After this step, the expert combines the two models to obtain a formal model of the production system. This model is verified using formal methods like model checking. After verifying this code, the next step is to transfer the code to the PLC, which will then control the physical system. However, formal design also has its own challenges, including complexity, time consuming, high expertise, which means that formal design require a deep understanding of formal methods and mathematical principles. And lastly, combinatorial explosion, which means that as the number of components increase in manufacturing system, the complexity to design a code for the system grows exponentially. Now, our objective. Given the challenges of both manual and formal design, researchers are now exploring artificial intelligence as a promising solution. This brings us to our objective, which is fully automate the process of code generation. So our approach starts with a manufacturing system. The experts only need to write a requirement specification that describe the system. Then AI models will process this requirement specification and they automatically generate the PLC code. Now for PLC programming languages, we can categorize them into two types. The first type is the graphical languages, and the second type is the textual languages. For graphical languages, there are ladder diagram, function block diagram, sequential function chart, while textual languages are instruction lists and structured text. Given the nature of our input, which is text-based input and output, we have two choices. We have instruction lists and structured text, and we selected structured text due to its popularity. Now, the method. We propose a multi-agent pipeline that converts natural language requirements into PLC code. So the expert will write a requirement specification and give it as input to an intelligent system. Given the complexity of the problem, we divide it into 3 subtasks using a divide and conquer strategy. Each agent is responsible for one specific task, and together they can generate the PLC code that respects the input requirement specification. Now I will explain the function of each agent, starting by agent 1 is the extraction agent. The extraction agent reads the requirement specification, find all sensors and actuators, the input and the output, then assign a PLC address to each one, and finally create an input and the output table. Next, we have agent 2. Agent 2 is the concurrent agent. It takes the requirement specification and the input-output table. Then it generates the local and global constraints. And finally, it creates a constraints table. Lastly, we have agent 3, which is the logic synthesis agent. It takes all the previous results and generates the PLC code using structured text. Results. So to see our approach, we take this example as a case study, which is a transfer station. This system moves boxes from one conveyor to another. The system includes conveyor number 1 to bring the boxes, conveyor number 2 to take the box away. Conclusion and future work. In this work, we proposed a fully automated pipeline that generates PLC program directly from natural language with no human intervention. Our future work will focus on, we plan to evaluate our pipeline on more industrial scenarios and measure the metrics like F1 score, accuracy, recall, and precision. Secondly, we aim to integrate formal verification such as model checking to verify if the generated code is correct or not. Thirdly, we will improve the logic synthesis agent to handle more complex behaviors. And lastly, we plan to test the system on real PLC hardware, moving from simulation to real industrial deployment. And thank you for your attention.